Hello guys, my name is Tu. So for this video, I will be demonstrating how can we perform a linear static analysis on an end effector on the robot. So let's go ahead by importing some external CAD data. So I'll be going to my end effector. I'll be importing the end effector.str.asm file from which is from SolidWorks. So I have this geometry with me. It is a simple geometry. So we have this component. Consists of two parts. These are the components, and these will be the base. Then yeah, so this will be a simple gripper. Okay, so let's move on to the Simcenter3D applications, and I will head over to pre-post. I'm going to directly create a new FEM and simulation file. So I will keep the default setting, which is to create an idealized path file. So to ensure that I preserve the hierarchy of the files. So I click OK. Oh, sorry, the solver is set to the wrong solver. So I will need to click close for now. Yeah, so notice that currently this will be my files that are loaded. So we have the sim file, we have the FEM file, the idealized file, and the original CAD data from SolidWorks. So these are all the SolidWorks individual files. So because just now I mistakenly chosen the wrong solver, so I will need to rectify that by right-clicking on this FEM, choose Edit. The solver I will need to change to uh, SimCenter NAS Run, and the analysis type is a structural analysis, and OK. So let's head over to the idealized path file. So in the idealized path file is where we do the geometry cleanup and some of the modeling stuff to ensure that the simulation can work as per normal while not interrupting the original CAD data. So the original CAD data is at this hierarchy, and the idealized part serve to preserve the originality of the CAD data by doing all the CAD modeling at this hierarchy. So for example, the first thing that I would like to do at this cleanup process is to add the bolts, because currently there are missing bolts over here. So I'll be just go ahead and creating some bolts. Okay, so first of all, I will go back to the modeling application in the idealized hierarchy. So here I will be creating curves, lines. So before that, I would like to show you that there is a setting called selection groups. So there is a allow automatic work path change. So this is a new behavior which is turned on by default. That everything that you every feature that you build is going to be built at the work part. The work part will automatically change based on your selection. For example, if I click the line, and when I try to click some objects over here, for now it is not possible because I have not toggled these filter from within the work part only to the entire assembly. So I need to choose entire assembly so that I can choose everything in within the assembly level. So let's say if I click once, you will notice that this particular component is highlighted while the rest is become uh, not unemphasized, because the part the work part has changed from the highest hierarchy to this particular object. So let's say if I continue to build my curve and I click OK, notice that the current work file is actually grip underscore link underscore 3, which is this particular work file, and this curve is built inside of this component at the path navigator here. So this is the latest behavior of the software. So let's say if I do do not want to create the line here, but I want to create my line at the higher hierarchy. Yes, I can do that, but I need to toggle this button over here. Okay, so I'll have toggled back to the older versions, older behavior. I'll delete the line. I return to the highest hierarchy, recreate the lines again. This time when I create the line, notice that there is no toggling of the path, and my line is actually created at the highest hierarchy. Okay, so I'll proceed to create all the 4 lines. Okay, so I've selected something. Okay, yeah, so this is the correct way to select the lines. Click here, select the center point, click apply. Click here and click on the center point and click apply. So now I have created 4 lines at the highest hierarchy inside the idealized part. So now the next thing that I would like to do is to create a dummy component. Let's say this gripper is gripping a dummy weight. So let's create a dummy component. So just cone maybe. So the cone is having a rough dimension as such. Anti in this, okay, as such. Okay, so this is the geometry. So to reposition it by using the Control key, I press the Control key, and I use the setting over here. Instead of creating additional duplicates objects, I just want to move the current object. So I use move. Let's try to toggle it to such. Show results. Okay, probably this is just an example. It is the gripping position of the dummy part. So the reason of creating this dummy part because it's just to demonstrate to you, we can try to extract the center of gravity of the dummy part for further downstream application because we need to we are not going to mesh the dummy part. We just want to use the center of gravity. So here, let's go ahead to create the center of gravity by going to Analysis and Go Measure. And we are going to select the object of this dummy geometry by, first of all, in the filter, we're going to choose solid bodies, select the dummy geometries, and notice that there is a computed center of mass, which is at these coordinates. We are going to click on this button here to create the point at the center of mass. So click OK, and notice that there is a symbol here that represents the center of the mass of the dummy weight object. Okay, now I'm satisfied with all the cleanup process. I'm going back to the FEM application. So go back to the FEM application and notice that the bolts, the nuts, the curves and the points are not shown because we have not enabled the options. We need to enable it explicitly by right-clicking on the FEM file, edit. So these geometry options, we can click here and we can click on the points and the lines and click OK. So if you have some coordinate system that you would like to bring in from the idealized part, then you need to click here to enable it. So click OK and click OK again. Now notice that I have my center point here and the lines as well. If I would like to, I don't want to import the dummy object. Yes, I can. So again, by going to the edit, so edit body to use. So this time I'm not going to select all visible, but I need to use the option select. I will deselect the dummy object and click OK. So now I will have the center of gravity, the curves, and the rest of the components. Okay, now let's go ahead and do the meshing operation. The first thing that I would like to demonstrate is use the 3D sweep mesh because this geometry is quite simple enough. So I can just go ahead and select all these simple geometries and do the sweep map. So first of all, as a trial, I will going to use automatic element size. So this is the 2.7. We can try immediately to divide by 2 to get a better estimation. And we're going to click apply and see what will happen. So this is the result mesh. I think it is quite nice. We see that there is the mesh that is covering the circumference of the hole. So this is a good quality mesh. There are at least 2 layers of mesh we see here. We need to make sure at least there are 2. If you only have 1 layer, then probably it's not good. It's not a good idea. So this is 2 layer, 2 layers. So this is good mesh. And we see that there is a circumference mesh that is covering the hole. So this is an indication of a good quality mesh. So now let's move on to check what have we achieved. So in the 3D collectors, we see that there is a solid 1 collectors that is collecting all the current existing mesh. So we need to assign a common material for all this mesh. So go ahead and double click on these collectors, and we can assign a material by going this edit button. So material, currently it is not assigned. Let's go ahead and choose a material from the default libraries. If you want to use other material, yes, you can by creating your own material from this button over here. But for now, I'm just going to use the steel material for the end effector. So I'm just going to say steel. So this is the steel. Now the next thing I would like to mesh I would like to use the tetrahedral mesh. So tetrahedral mesh, select this guy and this guy. Okay, so there are only 2. So we're going to choose the thunder. Click the thunder and divide by 2 will be a good estimation. I'm going to put this into the same mesh collector. So they share the same steel property. Okay, by visual observation, I see that the mesh is small enough, acceptable, and at least 2 layers. Okay, so this is a good sign of a good indication of the nice mesh. Alternatively, you can also check the mesh quality by pressing this button. But for now, I'll just move on. So the next thing that I would like to do is to create the connections, the both connections over here. I will use the 1D mesh button over here. So when I just press this button, you will notice that this line is highlighted with an arrow. This arrow is pointing down. So be careful. So which end that you are pressing. So let's say if I click this end, I will see that the arrow is pointing downwards. If I select the other end, you will notice the arrow is pointing outward. So this is one way to help us to define the direction of your 1D element. So in order to ensure the 1D element have consistency, all arrow pointing downwards, so I will just going to choose the top corner. So let's say if I choose the top corner here, you see that the arrow is pointing downwards. So choose the top corner, the arrow is pointing downwards, and so on. Okay, so 4 curves selected, and each of the curves will contain, let's say, 3 elements to give each of the shaft of the bolt will have 3 elements as such. And we are going to use C-beam to mean that this element is actually behave like a beam. So we use C-beam. So click OK, and we can track that inside the 1D collectors, we have the beam collectors, and this will be the mesh. So we can try, so we need to assign properties to this beam collector. For example, we need to assign the cross section, we need to assign a material. So again, double click on the beam collectors and click on the spanner. So we need to define a 4 section or the cross section. So we go ahead to the section manager. Currently, there is no cross-section defined. We create a new cross-section by clicking on this Create Section button. From the list of cross-section, we are going to use the rod because this is a simple cylindrical geometry. and the dim one is referring to the radius. So if you are unsure about what is the radius, we can try to do a measurement. So we can click the drop down over here and choose measure, and we are going to measure the so the you need to select the polygon H over here. So maybe polygon H. Yep. So the radius is 2.12. So we are going to assign this value. We can click on this plus button. So this will assign the value to return it. So this is the value. We can try to preview it. It looks like this. Okay. And okay. So the cross section is defined. Let's assign the material. So because previously we have loaded the steel, we are going to use the same material. So click here and click apply as well. Okay, so now let's try to display the beam by right-clicking on the beam collectors. We are going to change the color and show the cross sections. Okay, so changing the color to yellow, click OK, apply. So this now looks no, not yet. We didn't see the yellow yet. Okay, so this is the curve representation of the cross section. This is the solid representation, but I think curve is good enough. So we see that there is a yellow line along the radius. Click OK and accept the beam elements. So now let's try to create the connections between the bolt and the neighboring components. So this is done by using the 1D connections or the spider connections. We are going to use the associative method. Associative method means we are using the geometry associated method, which is point to edge in this case. So the point is referring to this point and the edge is referring to this edge. And we are going to use RBE2 rigid beam element, RBE2 in this case. And we are going to create a new collector to store this element. Click apply and notice that there is a new collector on here. Now let's continue to create the new definition. So this is the point and this will be the curve. And this time I'm going to put it into the same collector to make our simulation navigator more organized. So click apply again. So this will be the connections for the first bolt. Let's continue to do the same for the rest of the 3 bolts. So this apply and this apply. So same goes for here, this and this apply, this and this apply, this and this apply. Okay, so we have created the rigid elements. Let's try to create a different color. So edit the display. I would like to choose blue color for this case. So then we see that there's an update symbol over here. Let's press the update button. I'm not sure why, but we need to do the updates. Okay, so finally everything is ready. We have do the meshing. We have assigned material. We have assigned cross section. The mesh are ready. Everything inside the FAM should be ready to go. So I will just save my FAM and proceed to sim file. So I'm open up my simulation file to define the boundary conditions and the loading. Oh, sorry, I have not defined the connections and the load over here. So let's go back to the FAM file real quick, and we're going to define a weight, to represent the dummy product. So I drop down from here and I choose 0D mesh. I'll select this center point. Usually I like to use com m2, which is a simple definition. So I'll just use com m2 to define the weight of this dummy component. So in the 0D collectors, I'll expand and find the collectors over here, and I find my mesh over here. I need to assign the mass onto this particular node. So I'll just right click here and choose edit mesh associated data. The weight is maybe a 10 kilograms of dummy weight. at the center of gravity. So I'll just assign 10 over there, click OK. So assuming that this end effector is going to grip the dummy product and the contacting area is on these two surfaces, therefore I'm going to assign I will need to connect this dummy this dummy product weight to the contacting surface. So to do that, we can use the 1D connections, use point to face. So choose this point and based on the assumption that I made just now, there is a perfect contact to reach all the surface on this area. So if you think the contact is not on the face but is on the edge, yes, you can use a point to edge to do a better accurate representation of the contacting behavior. But in my case, my assumption is the weight is being perfectly touching on this face. So therefore, I'm using face. As for the type, I'll be using RBE3 because if you remember, RBE3 is more suitable for mass distribution based on proximity. If the center of gravity is closer to this node, therefore this node will have a higher weight, larger weight. If this node is further away from this contacting node, therefore this area will be lesser weight. So there will be a area weighted area distribution by using this RBE3. So if you use RBE2, that means all the nodes will have the same value. Yeah, so I prefer to use RBE3 in this case. So click OK. Yeah, so this is the weight definition. So we have defined this. Let's go ahead to the sim file. Okay, for sim file, we need to define the boundary conditions. So in order to simplify, we need to define the boundary conditions on the geometries because we are using geometry associations. Therefore, in order to simplify the selections, I will hide all my mesh. So I'll just go ahead and hide all my mesh here and only the geometry. So now I'm going to use constraint type. Oh, so this is the wrong because previously I have selected a wrong solver, so I need to create a new I need to rectify the solver first before I can continue to define my solution. And also notice that currently on the simulation file, it does not contain any solution. It only has the fan file and the rest of the item, but no solution. So let's quickly create a new solution. So new solution, I'm using the Simcenter Nasran instead of Simcenter3D ThermoFlow. So this is going to be a solution 101, which is a linear static. So I'm putting the name Sol101, creating the solution, and I'm going to accept the D file for now. I will edit it later. So this is my solution over here. And notice that once you created the solution, all the constraints are updated correctly according to the solution. So for this solution, I'm going to use a fixed constraint. So I'm just click on the fixed constraint now and click on those areas that I would like to fix. So assuming that these 5 surfaces are rigidly connecting to the robot. Okay, so click OK and OK. The next thing that I would like to do is define a gravity load. So let's say the gravity load is here, and the direction of the gravity is pointing in the y positive direction. So I'll choose y over here, click OK. And now it comes with the next part, which is contact and glue. So we can try to go ahead to the surface to surface contact and glue. So this is some new definitions over here which allow us to combine to toggle between contact and gluing quickly by using this definition. So we use this new definition over here. We are going to automatically do the assignment and see what we'll get. So we are going to use automatic and phase pair. So click phase pair. So, and I'm going to use polygon body. So polygon body, and I choose all the polygon bodies over here. There are total of 8. So the distance tolerance I put on 0.02. That means if the distance between the bodies are within this target, this tolerant distance, therefore a pairing is defined. If the distance is further away, let's say there is for example, if you see here, there is the geometries on this shaft is not so close as compared to the hole. Therefore, it is, I believe the distance here is already exceeded this tolerance. Therefore, there is no contact pair be defined at this area. So let's try and click OK and accept the default settings. And notice that there are 8 pairs, and we are going to accept the default setting. One particular setting that I would like to highlight to you is this maximum search distance. That means whenever the distance between the bodies is within 1 mm, therefore the contact is essentially effective, or the glue contact is effective. So I'll just click OK for now. Let's try to observe each of the contact individually, because this is quite important. So, okay, so we see that the first pair is between these two surfaces, and I think this is a makes sense. It makes sense. Okay, let's move on to the next one. Okay, so this is also makes sense to me. These two surfaces will contact or glue. Okay, so the third one is between this surface and this surface. So this is a contact. Yeah, it makes sense. So this is between this surface and this surface. Number 5, this surface and this surface. 6, this surface and this surface. So all this from number 3 to number 6 is a bit risky. You can say there is a bit risky because there is a tendency to fall. I mean, this component can fall off this surface because this is a contact rather than a gluing. Okay, let's look at number 7. So number 7 is between this surface and this surface. Number 8 is between this surface and this surface. So I would say the risky definition is this 4. Yeah, and 1, 2, and 7, 8 is considered stable. The reason why is because there is a both connections between the components already. So if you have additional contact definition, this is going to make the model more stable. Okay, so what are the lacking definitions? As you can see, there is no definitions on this hole. There is no definition on this hole, and there is no definition at this area as well, which will make it so there will be a tendency of this particular component to fall off this platform, even though this platform is constrained by the fixed constraint, but because there is no contact or there is no gluing at this particular area, therefore it is going to fail. It is going to fail. So to make things simple, I'm going to assign glue the contact or the gluing manually, because the contact pairs are not able to be searched just now. So let's do it again using the surface to surface contact and gluing. This time I'm going to use the manual operation, and I'm going to select it manually. So first I need to select the source region, which is this surface. Okay, this surface. Toggling the shaded view. I'm going very fast by holding the right mouse button to change the toggling view. Okay, so this will be the view, the face. Then this will be the corresponding contact face. Okay, so this is the contact. And what about the maximum search distance? Let's try to check what is the gap between these two surfaces in order to make sure that we want to have a contact or a glue. So let's try to do a measure. So I'm going to measure the points between the surface. So this is surface 1, this is surface 2. you see that this distance is 1.7. So 1.7 is actually quite huge over here, definitely able to cover this tiny gap. So, um, I think 1 mm here is sufficient to cover the gap over here based on the measurement just now. Okay, so therefore 1 is okay. I will just proceed and click apply. So remember that we are currently creating contact. So let's go ahead and continue with the next definition. Is and I'm going to accept okay, apply. And also at this area, and this area as well. Okay, so we have created 4 contacts to try to make the model more stable. So I'm not sure what will happens. Let's try to run the simulation. But before that, I'll just save. And I would like to also show you some of the settings inside the solutions. Let's go ahead to edit the solution 101 and go to the case control. Because we are using a lot of contacts and probably gluing, we are going to edit the output request to include the contact results. So contact result enable, and also gluing results enable as well. So far we did not define gluing, but probably later we need to toggle the contact to glue, and this will make sure the gluing result be captured as well. Okay, so we have that. And one more thing which is convenient. So let's go to the edit solver parameters. So because there are contact involved, and therefore you need more computational power. So depends on how many core you have on your computer. So I'm just going to quickly check my task manager for the cores. So for now, I have 8 core. I can use more cores to solve for this problem. Let's say if I put 6 core on this parallel area, so this will help me to run the simulation faster. Okay, so click OK, and let's try to solve the model and see what errors will I receive. So okay, so let's have a look into the conversion graph. So the contact we need to reach the convergence. So something is not sure what happens. Let's try to click on this these words and analyze draw information. Okay, so this is a very common error. So run terminated due to excessive pivot ratio. So this means that the mesh are floating in mid-air. The mesh are not stably connected between each other. The constraints are not enough. So we need to find out where is the mesh floating. So let's go ahead and close this dialog box and click cancel. We are going to head over to the F06 file, which is located at the working directory. So I'll just right click, select this solution and right click and choose browse so that I can go directly to my working directory. So this is my working directory. This is my F06 file, which is corresponding to this particular solution. I'll just right click this F06 file and open it with Notepad or any Notepad or text editor application. So for my case, I do have this Notepad++, which is quite convenient. So I'll just reload this model and search for the word fatal. Fatal, okay, so we see the fatal message over here. So this is the same message we received in Simcenter3D, and these are the nodes that are floating. They are floating. So let's check the first node, uh, 3822. So we go back to my application. For now, I will need to uh, show the 3D mesh, 1D and 0D. I need to show everything, and I go to the nodes and elements, information, search for the node label 3A22. Before that, I would like to hide all my definitions. Okay, so this is hiding all my definitions to make my view clearer. Apply. Okay, I didn't see anything, but if I change to wireframe with theme edges, I'm able to see it is actually over here. Okay, so there is some probably this gear mesh is not stable. Okay, so that's the first hint. So let's check the other one. 4078. 4078. Again, it is located here. Then 5143. 5143. Okay, so it's also here as well. So my probably this node is referred to the second gear over here. So in order to simplify the problem, we can try to uh, define some connections between this mesh and also this mesh. But in order to simplify the demonstration, I'm going to quickly toggle this contact into a glue contact rather than a surface contact. So I'm just going to select this guy over here, and I'm toggling the contact into glue. But probably the actual practice is probably you need to add think of ways on how you want to have a better representation of the contact in this area. Uh, Maybe by adding a clip to restrain the motion, or to add additional constraint on this surface and etc. So these are some of the things that you can try. Or maybe you want to build some 1D connections between the shaft and also the hole. So these are some of the possible solution, possible actions. But for now, in order to simplify the demonstration, I'm just going to change this to glue. That means this particular, so let me just turn off the mesh for now. That means for this particular area, the highlighted surface are super glued together and behave as one single part. So that's the meaning of gluing. So let's try to rerun the solution again and see how it goes and if there's any errors. Okay, so the solution has end. So we see that in the last iteration, we see that there are total of these inactive contacts. That means there are essentially no contact between the contact pairs. And there are some sliding contacts, but there is no sticking contact. The reason is because we did not specify any coefficient of static friction. If we do specify the coefficient of static friction, for example, at these contact pairs, uh, okay, so we see that currently the coefficient of static friction is 0. Therefore, sticking is not possible. Therefore, we simplify the sticking. Therefore, there is no sticking whatsoever. Only that there is some sliding contacts as such. So now let's try to look into another the diagnosis. Select here and check on the the analysis job information. There is no, the good news is there's no fatal, and there is some warning, however. Okay, so let's try to check the result now. So results, displacement. Okay, so I'm not sure. Seems like the software has crashed. I'll restart the simulation and read again. There's some error over here. Okay, so let's try to restart the simulation. I mean the start the software. Probably this is an unstable version. Uh, okay, so opens recent file. So opens. Uh, so this will be my file just now. Click OK. Okay, so uh, let's try to solve again. I'm not sure what will happen. So while it is running, I'm just quickly checked all the definitions. So this is a blue, okay. Okay, so let's check the results again. So displacement, okay, we see that there is a displacement result and stress. So these are the stress results. So for stress result, I would recommend you to use the average options. So this will be a more accurate in 3D mesh. So contact force. So these are the contact moments, contact pressure, glue force. So these are the area which is glued together. Okay. Okay. So yeah. So you can try to toggle the external and features so to make it more nicer. So this is but this is also an exaggerated displacement. You can change to absolute percent. Okay, so this is the actual displacement. Then you can try to maybe toggle back to 10%, and do the animation. So these are the animation. You see that there is a possibility of sliding going on over here, but because we define the glue contact, therefore this is more stable. And so this concludes my demonstration. I hope you enjoyed it. Thank you very much.